Right, this is the core practical, this is the required practical where we investigate Newton's second law of motion. Right, the mass that is to be accelerated is this cart. Alright, it says collision cart there, but we've only got one of those. It's on wheels and it goes on this custom made track like this, and it's a very low friction track. The force that does the accelerating, well, we've got string attached here, and as you can see the other end, we've got some slotted masses hanging over a pulley. Okay. Right, now the force that does the accelerating force is the exact weight of the slotted masses. Now we can calculate the exact weight of that using W equals mg, not forgetting to convert grams to kilograms. Right, so that's the force, the exact weight of the slotted masses is the force that does the accelerating. Okay, so the mass is the cart, the force that does the accelerating is the weight of the slotted masses. Now, how to measure accurately and precisely the acceleration? We're going to use these fellas. These are called light gates. We've got two of them. Now, what light gates do, they're a very clever way of measuring the speed, the exact speed that an object moves through. Okay. Now these two light gates are connected wirelessly to a laptop that's running the special data logging app called SparkView. Okay. I'll just come from a slightly different angle, which is going to make it easier for you to see and understand how light gates work. Right, as you can see here, we've got these two horseshoe-shaped things here. Now what a light gate is, there's a beam of light that goes from one side across to the other, and there's a sensor on the other. And as you know, light travels very fast. It certainly travels, or takes a very short time to go across a small gap. Now, this is the clever bit. When an object, in this case, we've got the cart, will have attached to it a piece of card that's exactly 10 centimetres, exactly 100 millimetres wide. When that goes through the light gate, the instant it breaks the light beam, that's recorded and sent to the laptop. The instant the card leaves and the light beam comes back, that exact time is communicated to the app. And the app literally just subtracts the two to calculate the exact time it takes for the card to travel through the light gate. Okay. Now the app also knows that the card width is exactly 100 millimetres wide, and it simply does speed equals distance over time to find the speed at which it's travelling when it passes through. Okay. Now we've got a second light gate here, which does exactly the same thing. So calculate the speed here, final speed v, initial speed u. The light gates also communicate the exact time between the two light gates. Okay, so it does v minus u divided by t to give the acceleration. So the average acceleration as it's travelling along the track. Okay, quite straightforward. Right, let's just put you back to the original position. Right, just a couple more things to explain. Now, there's a slight complication here. We've got the force, which is the slotted masses, the weight of the slotted masses. We've got the acceleration measured with these two. Now, what exactly is the mass that is being accelerated? Well, obviously this is the main thing that's being accelerated, and this is going to have mass. However, the slotted masses on the end also are being accelerated by the weight as well. So we have to take the mass of this, plus the string, plus the slotted masses as our mass, that has been accelerated. Now, in this experiment, F equals ma, there's two parts, because that's three variables, force, mass and acceleration. Now in the first part, I'm going to vary the force. I'm going to vary the accelerating force by varying the amount of slotted masses. The dependent variable is going to be the acceleration, which is going to be measured. Now the mass, we want that to be a constant. We want that to be a control variable in the first part of this experiment. Now to do that, we need to keep mass constant. Now to do that, we have to keep the mass of the whole system constant. So the mass of the cart plus the string plus the slotted masses has to remain constant throughout this practical. Now the way we get around that is, if we're going to add slotted masses to the end, we have to take them off this cart here. So I've got 20 grams there. I've actually got 1, 2, 3, 4, 5, 6, which each time I'm going to take one off here and put it on the end there to increase the accelerating force. But because I'm taking them off here, that keeps the mass of the system constant. Okay? Quite simple really. These slotted masses, these big 100 grams here, they're just to stop this flying off until I'm ready. Now one last thing, okay? Because we want to see the effect of only the accelerating force, okay? Because there's other forces acting on the trolley, there's obviously going to be friction. Now friction's going backwards. Now what we need to do before we start is we want to friction compensate the ramp. Now let me explain. At the moment, let's just take the slotted masses off for now. At the moment, the trolley, the ramp rather, is horizontal. Now if I let the trolley go, because of friction it should slow down naturally. Let's just start this recording. Right, I've set up my data logger here. I've set up the app, just getting a nice combination of colours for you that can be seen in the video. That'll do. Right, there's 4 numbers here. We've got initial speed U, final speed V. This is the time between the 2 light gates, and this is the calculated acceleration. Now, we're ready to go. If we push it through, we can see a negative acceleration. That's because it's slowed down. That's because we've got the resultant force acting on the cart after I've pushed it is backwards. So it's going to slow down. So what we do, we make it higher at this end. So we give it a very, very gradual downward slope that should negate the effects of friction. Okay? Let's see. Very close, but still we have a very, very small deceleration. We want this to be 0, don't we? Okay? Oh, so I'm going too far there. So if we make that 0, that means that the only force, that means that once I push it, the only force, or once I push it, the resultant force is 0, so there's going to be 0 acceleration. Let's try that. Boom. Right, that'll do. We've now friction compensated the ramp, so that once it moves, or when it's moving at a constant speed, it will stay at a constant speed. Okay, we're ready to go now with our first data point. Okay, we've got 20 grams of slotted masses. That's going to be producing the accelerating force. Right. First data point. So, acceleration. first value of acceleration, 0.34 meters per second squared. Now, because we want to add a 10 gram slotted mass to the end, we have to take it off here. Okay. So now we've got 30 grams of slotted masses. Okay. Next acceleration. 0.52 meters per second squared. Next up, one more. Off the cart, on to the end. So we've now got 40 grams of slotted masses. Next acceleration. 0.69 meters per second squared. One off. Now I've got 1, 2, 3, 4, 5, 50 grams of slotted masses. New acceleration is 0.87 meters per second squared. One off, and onto the end here. So now we've got 60 grams of slotted masses. We'll produce an acceleration of 1.06 meters per second squared. Okay. Penultimate data point. We've now got, good job on counting, one's dropped on the floor. Right, 1, 2, 3, 4, 5, 6, 7. We've now got 70 grams of slotted masses on the end. Okay, the acceleration here is 1.25 meters per second squared. Finally, last one off. Last one off. And on to the end. So we've got 8. We've got 8. 1, 2, 3, 4, 5, 6, 7, 8. 80 grams of slotted masses. Now that's giving us an acceleration of 1.44 meters per second squared. Okay. Well, one last thing is, let's go back to our control variable here. Okay. Now, our control variable, like I explained, is the mass of the system, the total mass of the system. Now, I'm going to measure that, because that will come in quite useful with this experiment after we plotted the graph. So that's our whole system, yeah, the cart and the slotted masses. Now I'm going to measure that accurately and precisely on a top hand balance. Okay. Right, guess you want a closer look at that. So, there we have it. That's 580.6 grams.